Stoichiometry. Now, we need to understand that when we have a balanced equation, it provides the same kind of quantitative information that a recipe does. A balanced equation is basically a recipe. The reactants is what all your ingredients beforehand, and then your product, once you put all the ingredients together, that's what you get. If we look at a balanced equation for a cake, so we're going to make a cake. We need 1 cup of flour for this cake, 4 cups sugar, 3 sticks of butter, 2 chocolate chips, and 15 slices of bologna. Going to have a nice tasting cake here. Here's the equation. So we have the 1 cup of flour, the 4 sugar bags, the 3 sticks of butter, the 2 chocolate chips, and the 15 bologna. And what do we get? We put them all together and we get 1 cake. So these will all react. We heat it up in the oven, we mix it, and we get 1 cake. Now, if we double the recipe, such as 2, 8, 6, 4, 30 pieces of bologna, we'd get 2 cakes. But because we just have this is for 1 cake. Now let's say for the charity ball you have volunteered to make 25 cakes. We want to know how many sticks of butter do you need to get from the store. So let's look at this equation. We can look back at the equation and we see the butter is here. This is for 1 cake, and we can figure out if we have 25 cakes, we're going to have 25 times this, so that's going to be 75 sticks of butter. 75 sticks of butter. Also 25 cups of flour, 100 bags of sugar, etc. So with our balanced equation, we can see exactly what ingredients we need. If for whatever we need on one side, we can calculate it if it's balanced. So stoichiometry, this is all stoichiometry. This is a very important chapter. This is important stuff. This is chemistry basically. Now it's really, this is chemistry. Now stoichiometry is Greek, as you probably know, and it means measuring elements. I'm sure you guys knew that. The calculations of quantities and chemical reactions are based on a balanced equation. So of course we have to have a balanced equation in order to do this. We can interpret balanced equations in several ways. So we have this equation that's balanced. We can look at it as a number of atoms at the atomic level. So if it's just an atom here, a number of molecules, so here we have molecules, formula units. So for instance, we can say this is 1 molecule of nitrogen gas, 3 molecules of hydrogen gas, 2 molecules of ammonia, or NH3. So we can look at a chemical equation as just looking at molecules or individual atoms. So here's another one. We can have 2 molecules of hydrogen and 1 molecule of oxygen to form 2 molecules of water. Another one here, we have 2 formula units of aluminum oxide. Will form 4 atoms of aluminum and 3 molecules of oxygen. Here if we have 2 atoms of sodium, 2 molecules of water form 2 formula units. So remember, formula units are for ionic bonds. NaOH and 1 molecule of hydrogen gas. Now we can look at it differently too. The same equation, but we're not going to look at it as individual molecules. Let's say we're looking at dozens. So we have 2 dozen molecules of hydrogen, 1 dozen molecules of oxygen to form 2 dozen molecules of water. So these coefficients can represent really anything. But we know, so we can say 2 times 6.02 times 10 to the 23rd molecules of hydrogen times 1 times 6.02 times 10 to the 23rd molecules of oxygen form 2 times 6.02 times 10 to the 23rd molecules of water. Now that, of course, means moles. Usually what we do in chemistry, we don't look at individual atoms, we look at moles, because individual atoms are just too small to deal with. So we're going to look at moles. 2 moles of hydrogen plus 1 mole of oxygen form 2 moles of water. Moles are big. They represent a lot of molecules, so we can really, that's something we can handle. In terms of moles, this is what we're dealing with here. We have 2 moles of aluminum oxide goes to 4 moles of aluminum plus 3 moles of oxygen. The coefficients, those numbers in front, will tell us how many moles of each kind. So when we see a balanced equation, we're going to look at these as being moles. That's important when we start doing stoichiometry. Now in terms of mass, we have to know that the law of conservation of mass will always apply, and we can use this and check by using moles. For example, here we have 2 moles of hydrogen. Now 1 mole of hydrogen is 2.02 grams. So this equals 4.04 grams, and we know that. We've done that already. Now 1 mole of oxygen we know will equal 32 grams. So the mass will be conserved. And we've already done stuff like this. But what we're looking at here is the reactants, the water, is going to be conserved. This is the reactants. 36.04 is H2 plus O2. And that's the same number that we should get when we add up H2O. And there's a little thing that wasn't too exciting. So in terms of mass again, here we have 2 moles of water. So we calculated that we have 36.04 grams in the reactants. And what about in the products? We calculate the mass to be 36.04. Mass is conserved. And there we go. It shows us mass conserved. Very exciting. So we're going to do mole-to-mole conversions first. Meaning how many moles of one thing will give you how many of the other. So we need to look at our balanced equation. So every time we use, what this equation says, every time we use 2 moles of aluminum oxide, we make 3 moles of oxygen. Okay? 2 moles here will give 3 moles. And also 2 moles of Al2O3 will give 4 moles of Al. 3 moles of O2 will give 4 moles of Al. 4 moles of Al will give 3 and 2, etc. So let's look at these. These are all mole ratios. So we need to understand that mole ratio of 1 mole to the other. So for instance, we have 2 moles of Al2 is to 3 moles of O2. Or 2 moles of Al2 to 3 moles. Erase that. So we have mole ratios here. And of course we can put Al in there as well. 4 moles Al is to 3 moles O2 and vice versa. We can flip that. We can write it any way because they're all equal. The ratios will be equal. Now we get to the fun part, the problems. Mole-to-mole conversions using mole ratios. So we're asked the question, how many moles of oxygen are produced when 3.3 moles of aluminum oxide decompose? Now we have to look at our balanced equation here. We start with 3.34 moles. Al2O3, and we just multiply it by a mole ratio. So what is the mole ratio? What do we want? We want oxygen. So we use our mole ratio. We want oxygen, so oxygen goes on top. So we have 3 moles of oxygen divided by 2 mole of Al2O3. And the moles of Al2 cross out. We're left with moles of oxygen, and we get 5.01 moles of O2. So that's what we get if we have 3.34 moles of Al2O3. Now let's look at this example here. We have this combustion reaction. If we're asked if we have 3.84 moles of C2H2 and we burn that, how many moles of oxygen do we need in order to burn that many moles of C2H2? We start with what we're given, 3.84 moles of C2H2. And what is our ratio? We go with a mole ratio in the middle. And we want O2 on top, so we'll put that. We have 5 moles of O2 from the equation. So this mole ratio is from the equation. And that is to 2 moles of C2H2. Moles will cancel out, and we'll be left with 5 moles of O2 times 3.84. That equals 9.6 mole of oxygen. That's how many moles of oxygen we need to burn 3.84 moles of C2H2. We want to see how many moles of C2H2 are needed to produce 8.95 moles of H2O. So we're just going to go from mole to mole. So we need moles of water. So the mole ratio, and then we'll get moles of C2H2 of 8.95 mole of water times the mole ratio there. The mole ratio is 2 mole of water. Now we want that on the bottom so it cancels out, and we want 2 mole C2H2 on top because that's what we want. We want to get C2H2. Now, of course, this is going to cancel out, and we're going to get 8.95 mole of C2H2. Now, you don't even have to do this. If you can figure it out directly from this, you don't have to actually do this whole thing. If you can figure out in your head, just do that. But you'll have more complicated problems where you will have to do this mole ratio equation. Now, we really can't directly measure moles. There's no scale or balance that we can just directly measure moles. So what do? We have to, what can we do? We can convert grams to moles through the periodic table, and then we can use moles to change chemicals. We can balance the equation, and then turn the moles back to grams using the periodic table.